Good morning. We are moving on with Chapter 3, and so we did a really thorough look at Chapter 2. We're through, kind of halfway through Chapter 3 right now. Make sure you're doing the homework problems. Make sure that you are looking at the examples, that you can independently set up these problems. It's great to work together in a group with other students and check different kinds of resources in problem solving. At the end of the day, you want to make sure that you independently can solve these. So if you've worked together in a group solving the homework problems or some of these examples, make sure that you go back afterwards, maybe set things aside for a few hours is often enough, maybe the next day, and then see if you can work through independently in setting things up. Well, we had finished off with this example in projectile motion, so we were looking at projectile motion. We had a 50-meter high cliff, kind of our standard 50-meter high cliff that we seem to have in a lot of problems, and we're trying to drive off that cliff at a high enough speed that we can land crash safely 90 meters from the base of the cliff. That's where the cameras are set up, ready to catch this landing. And so what we had done is we had drawn a diagram. Now, I have this kind of personal preference. It's not a big deal, but I like to just designate my given information as something different from x naughts and y naughts. So I started out by saying the 50 meters, I'm going to call that a height. The distance downrange is 90 meters. X naught I set equal to 0, y naught I set equal to h, and then we brought out our formulas for constant velocity for the x direction and then constant acceleration in the y direction. So that's what we have for our formulas here. And then coming over to here, I substituted in the d's and the h's. And I've used, so this really is where it kind of comes down to kind of staring at the formulas that you're working from and going, how do I proceed? And the idea here is, I don't know time. I don't know how much time it's going to take to drop. So how am I going to find out the amount of time? Because to find out, let's think of it this way, to find out the V naught, that's what I'm after. It should say up here, V naught is equal to a big empty box, because I got to fill that in. So V naught is D over T. Now, I know what D is. D is 90 meters, but I don't know what T is. And I don't see any other formula. There's not any formula on the Y side that has V naught in it, so I've got to somehow solve this equation, and that means I've somehow got to find the time. So if I move over to the vertical direction and I ask, is there a way in the vertical direction I can find out how much time it's going to take to drop and impact with the ground? And there is. So I know the height, and I know the gravitational field of the Earth. I'm assuming this is being done on planet Earth, that they haven't moved to a different location. It's not the moon. The moon would be really handy because it would get rid of the air resistance. So if it were the moon, the air resistance would be a non-issue. The gravitational field would be different, but the moon would take care of all of the air resistance issues that we keep mentioning. So time here, we can calculate using the formula 2h over g. That's going to allow me to calculate time. If I drop from 50 meters with an acceleration of 9.8 meters per second, that's going to require 3.19 seconds. So once I know how much time is involved in the drop, I can plug that into my V naught formula, and that tells me I'm going to need to travel at so I've got 28.2 meters per second. So I'm going to be looking at my speedometer, right, coming off the cliff. And I got to make sure my speedometer is at 28.2 meters per second. I got to get one of those speedometers that reads in meters per second. And head off the cliff. I've always wanted to get one on my car so I could just do meters per second. So I'm going to come off the cliff at that speed, and again, it's going to be 60, 65 miles an hour or something like that is the speed we got to drive off the cliff. no problem, right? Just projectile motion. All right, here is a kicked football. So it's another example, projectile motion. This time it's a little more complicated because we're starting at the ground and we're angling this at 37 degrees. And so I now have initial components in the x and initial components of velocity in the y. Everything else is kind of the same. So a football is kicked at 37 degrees with a speed of 20 meters per second. So 20 meters per second, what was that? It was like 45 miles an hour, something like that. We want to find out what's the maximum height. Now, the height is identified because the speed in the y direction goes to 0 at the top. So that's going to be identifiable. The time of travel for the whole trajectory, so how much time is it in the air, what's the hang time on this, and how far downrange is it going to land, the velocity vector at the maximum height, and acceleration vector at maximum, assume the ball leaves the foot. Okay, so the ball is leaving the ground right at the ground level, so it's kickoff, and it's going to land on the ground, so that's good. We're starting and ending at the same elevations. You know, any simplification at this point that we can come up with is going to help. So here is my diagram, and here is the football being kicked, being launched with V naught and theta. Now let's write some stuff down here. I'm going to say x naught is 0 and y naught is 0. It seems like we can get away with that, and that's going to simplify our formulas. Now the given information is V naught is 20 meters per second, and the starting angle, the initial angle, is 37 degrees. I tend not to write theta naught. Maybe I should, because theta is going to change. It's going to start off at 37 degrees, however. So here's what my formulas look like. X naught is equal to 0. So when I look at my constant velocity formula, it's V naught x times t, or Vx naught. Either way, they're the same thing. So V naught x is going to be V naught cosine theta. And so I wrote that out. So instead of leaving this as V naught x, now this form may be more useful, or maybe this will be. Since I know both of these, I guess it doesn't matter that much. So I can get a V naught cosine theta into my formula. Now in the y direction here, I'm going to have V naught y times t minus 1/2 gt squared. And that can be rewritten, I rewrote this, as V naught sine theta. Again, depending on the problem that you're given, sometimes it's easier to work with component form, sometimes it's easier to work in terms of the cosine and the sines. In this case, they gave me the 37 degrees, so I went ahead and wrote it, the angles in. And then the Vy, now this is an important formula for us, remember, the Vy is going to, the Vy is going to get used to tell us when we've reached the top of the trajectory. So this is going to be V naught sine theta minus gt. Now I didn't write down the Vy squared formula, and I'm just thinking maybe I should have. That probably would have been easier to solve part A. Part A was the maximum height, right? So I ended up doing it in 2 steps, but I think I could have done it in 1. Now, I do like the fact that we're solving here in part A. We're going to solve for the time. How much time does it take us to reach the top? Because that information is going to be useful later in the problem. So, you know, it's kind of a 50-50 as to which approach we want to apply. But I'm going to go ahead and say this. So at point B, right at the top of the trajectory, I'm going to have Vy is equal to 0. Now that says that if Vy is equal to 0, then we must be in the condition where g times t equals V naught sine theta. And so that's what I've written. V naught sine theta equals gt. And that means I can go in and solve for time. So I plugged in all the numbers that I was given. 20 meters per second, 37 degrees, 9.80 meters per second for the gravitational field. And from that, I was able to come up with t. And I solved for t, and it says, oh, it's going to take 1.23 seconds to reach the top of the trajectory. So I'm thinking, does that seem reasonable? I've watched footballs at kickoff. And you go, sure, why not? So the ball is kicked, and it's going to take 1.23 seconds to reach the top. And right now, before we continue solving part A, how long do you think it's going to take to come back down? And what we found in those previous problems is if we neglect air resistance, it's going to take 1.23 seconds to come back down. So we already kind of have an idea of how much time it's going to take to reach point C. Now I went through and solved that separately. But anyway, I've got the time now it's going to take to reach the top. Now once I know the time, I can plug that into my Y formula. And I did that. I plugged it into the Y formula. And I was careful. There's a lot of stuff going on here. It came through as 7.39 meters. So 7.39 meters, that's going to be like 25 feet in the air. So 7.4 meters of height. Sure, that seems reasonable enough. And so I'll write that down. I'll walk in that answer. So part B says, how long are we going to be in the air? Now, there's another way we could solve this. Part C is characterized by y is equal to 0. Because it came back down and it hit the ground, and with the coordinate system that we've set up, that corresponds to y equals 0. So y equals 0, well, y naught equals 0 too. So if y equals 0 and y naught equals 0, then what I'm going to get is this formula where v, because this is 0, v naught sine theta t equals 1/2 gt squared. So that's what I wrote down. And then I factored out a TC. And the remaining formula says that the time at point C is given by 2 v naught sine theta over g. Oh, look. The formulas are telling us something that we thought was probably true. And that is it's going to take just as much time to come back down as it did to reach the maximum height in the absence of air resistance. So we gotta, again, we gotta kick this football on the moon to make sure that we're neglecting air resistance. So, oh, that's it. So for part B then, we've solved part B, we've solved part A. What are the kind of things that they want to know about? We're looking pretty good here. Let's see. How far have we, of course, how far down range, that's going to be really important. So we can come back and say that the x formula is just constant velocity. That's v naught cosine of theta times t. I can plug in the full 2.46 seconds, and it says that after 2.46 seconds, we should have traveled in the x direction, the downrange direction, we should have traveled 39.2 meters. So 39.2 meters, that's going to be more than 40 yards. So it's better than a 40-yard punt, or not a punt, it's a kickoff. So that doesn't seem very good then, right? Anyway, probably not NFL kind of stuff. So 39.2 meters downrange where this is landing. So, all right, and then finally at point, well not finally because there's part E, but the first finally, part D, at point B, how fast are we traveling? What are the components of the velocity at the highest location? And so what we can do now is, well, we know what Vx is, that wasn't hard. Vx is v naught cosine theta, Vx is that the whole time. So the football is consistently moving in the x direction at 16.0 meters every second. As long as it's in the air, and we neglect air resistance, we're going to keep coming up with that 16.0 meters per second number. Now, in the y direction, we know it's 0. So the speed now has dropped to 16 meters per second. When we first launched it, when we first kicked the football, it was moving at 20 meters per second, but it's lost all of its y component. So the y component is gone. All that's left is the x component. Now, what about the acceleration components? Well, the acceleration's constant. They threw in a trick question here. They said, what's the acceleration right at the top? Now, throughout the entire path, the entire trajectory, the acceleration in the x direction is 0. We're assuming no air resistance, and so the speed in the x direction, under those circumstances, would be constant. And so the acceleration in the x is 0, whereas in the vertical direction, the gravitational field is going to maintain a constant acceleration of 9.80 meters per second downwards. And so that's what's happening in the y direction. So those are my acceleration components. So that's it. Okay, I think we got it all. This is a good problem, right? It's got A, B, C, D, E. You know, this could be a midterm problem. Plenty of different things to look at. Okay, so let's continue on with projectile motion, trying to get kind of a better feel for how we work with projectile motion. So here's this person in a wagon, and they're throwing some object up in the air, and it goes straight up, and then it comes back down. And then the question is, what happens if, oh my gosh, this wagon's going really fast. So the wagon now is going to be moving along at some constant speed, and when the person throws this up, in addition to the vertical velocity, it's going to have a horizontal velocity, and the horizontal velocity will stay constant. So if air resistance truly can be neglected in this example, then what we would expect to find is that as this thing goes up, it's moving forward at the same speed as the wagon, right? The person in the wagon didn't intentionally give it any forward speed. The person in the wagon just threw it upwards, same as they were throwing it before when the wagon was at rest. But now what we've got is, because of the motion of the wagon, the projectile, the ball, will have that forward motion, and it's just going to stay right above the wagon all the way over to here. Oh, that's pretty cool. She just caught it, right? Just like she threw it up, and then she put her hands out, and if there's no air resistance, it should move forward with the same speed, and it just ended up landing right in her hands over here. So that's a prediction, and it's a good prediction for the case where air resistance has been a small effect. So conceptually, that's what is going on in that example. Okay, here's another example, kind of related. So let's see, there's a water balloon slingshot being fired. So here is the water balloon coming off of this firing device for the water balloon. So here someone's hanging from a branch in a tree, and the person firing is aiming right where the person is located. Now, we're not sure if either of these persons have taken physics, if any of them have, what their understanding of projectile motion is. Hey, if you're outside, if instead of staying inside and reading physics books, if you're outside trying out water balloons, you may have learned a few things there too. So this water balloon is going to get fired horizontally. Now the intention, I guess, is for it to follow a straight path and run into this person, but that's not what's going to happen. What's going to happen is the water balloon is going to be pulled downwards by the force of gravity. That's going to create a downward acceleration. So if you're going to hit the person, you're going to have to fire it real fast, because as time progresses, it's going to drop depending on how much time has gone by. So it looks like, at least with the diagram shown here, that this is going to miss the person because it's dropping below. Oh wait, the person let go of the tree. Oh, okay, so what happens in this example, if you go back and read all these details, it says that the person anticipated, right at the time the person fired, this person let go of the branch. Good reaction time. I don't know how the person did that. I thought there was a half-second reaction time we had to deal with, but apparently this person was able to let go right at the instant when it was fired. Oh, wait a minute, both objects are going to fall at the same rate in the gravitational field. That means that this is going to land right on the person. So the person dropped and ends up getting hit. So, you know, it's... So if you'd studied physics, how would your response be different here? If you had studied physics, would you just hang on to the tree with the assumption that if you look and see the person firing directly at you, you could say, yeah, but gravity, there's no way it's going to reach me, because gravity is going to pull it downwards, right? Or the person firing, right? The person firing would adjust for this and say, you know, if I'm going to hit that person, I'm going to have to aim above and then let gravity bring the object to its target. Anyway, for both of them being released at the same time, the person and the projectile, they'll both drop together. So that person is going to get hit with the water balloon. All right, let's do this. Let's take a look with projectile motion. We like projectile motion. It's such a good example for working in 2 dimensions and understanding gravitational accelerations, constant velocity, constant acceleration. There's just a lot of good concepts in here. So let's do this. Let's say that we launch something from some point. We're going to label that the origin, set up our coordinate system. And when we launch it, we're going to get this nice parabolic shape trajectory. Now, if it lands right at the same elevation that it was launched at, then it would be nice to come up with a range formula. Now, we already did this in the last problem. If you think about it, we solved for range. We said it was going to land 39, 40 meters downrange. How did we do that? And we did it in a couple of steps. And so what they want us to do is retrace those steps, and this time keep it as a formula for horizontal range of a projectile. We want the range to be in terms of the initial velocity and the angle theta naught. So we want this in terms of v naught and theta naught. Those are the values that we want our answer in terms of. Okay, so down here, I think this is useful right here, right? This is kind of useful to think about. There's going to be some angle that probably gives us the longest downrange distance, and they're suggesting maybe it's 45 degrees. We'll try that and see if it really works. And then they're saying, look, for other angles, we know that if we go really high, it won't go as far, you know, from experience with throwing things. And then if we want to throw something at a lower angle, it's just not going to be in the air very long, and so it's going to hit the ground sooner, and that won't go very far either. So it looks like there's probably an optimum angle to fire things, and if we vary from the optimum angle, we're going to land short. Now, they're suggesting that launching at 60 degrees or 30 results in the same range, the same distance. So let's check this out. I'm going to read everything carefully, but I also want to get done before tomorrow. Let's see. What? Okay, these are Napoleon's cannons. They have a muzzle speed of 60 meters per second. What angle should they... Oh. So it's not quite that simple. We want to hit something 320 meters away. We have a launch speed of 60 meters per second. Now, on the one hand, cannons with their projectiles, you know, a cannon projectile, it's dense and it's pretty heavy, so it's pretty good sized. Maybe air resistance isn't a big deal. I don't know how important air resistance is. Maybe this is a good example. 320 meters, that's a good distance. So we're really trying to hit way down range. Let's see how this is going to work. So here we go. Projectile motion, horizontal range. Let's get that formula developed. Now, if you remember, I'm going to call this D, which, oh, I kept D. I should have used big R for range. Oh well, so I'm using little d. So little d is equal to Vx cosine theta, that's our x velocity times time. This is how we solved it before. Now what we need to do is find out how do we determine how much time it's in the air. Now if you remember, if we said y, the final y value at point D is going to equal the same elevation as point A, then those two drop out of the formula, and solving for t, we got 2 v naught sine theta divided by g. Okay, so that's what we ended up with for solving for time. Well, I can take that amount of time, plug it in for t, and what we will now have is our range formula. The range formula says traveling at this speed for this much time means that the distance we travel downrange is going to be given by v naught squared over g times 2 sine theta cosine theta. Okay, now that formula looks fine, except it's a little difficult to see exactly what's going on. And the reason why is it has a factor of sine theta and it has a factor of cosine theta. It's got both. It's got a factor of each one. And so it's hard to know what the sine theta times cosine theta function looks like. So what we do is we take a trig identity. I don't know if you guys probably learned this in a trig class somewhere. 2 times sine theta cosine is the same thing as the sine of 2 theta. I tell you, these trig identities, they're just amazing. They're just miracles. They're impossible to remember for myself. But there's just an amazing set of identities that are possible using trig functions. Anyway, 2 times sine theta cosine theta, if it's sine 2 theta, let's substitute that in instead. So now I don't have 2 factors of angles, I just have 1. And I can just take 2 times the angle and then multiply by sine, and there it is. There's my range formula. So it sounds like what we want to do is put in the range. What was it, 320 meters? We wanted to hit something? That's a long way. And the launch speed is going to be 60 meters per second, and it sounded like this is being launched at the surface of the Earth. And so the gravitational acceleration value we're going to put down as 9.8. So here it is. So I took the formula. Let's see, what was the where'd the formula go? I didn't bring it over. I might have to go back. We might have to jump back and forth a bit. So here is the formula. Memorize it. Now we'll switch back and forth. So the formula is d v naught squared over g. Now it's the sine of 2 theta. So we can already start seeing how would I get the maximum range. And the maximum range would come from maximizing sine 2 theta. So if we ask, I've got a certain muzzle velocity, the projectile is going to come out of the cannon at a certain speed, 60 meters per second. How would I get that to go as far as possible? And that would mean we want an angle of 2 theta equals 90 degrees. It turns out 45 degrees is the best angle. 45 degrees is the optimum compromise between giving it a lot of velocity downrange and keeping it in the air long enough that it goes downrange. So at 45 degrees, we're going to max out that. So what we could do is say d max is given by v naught squared over g, assuming that d max we're going to be launching at 45 degrees. So that much seems to be working. So that's what I've done here. What I did was I took the v naught, 60 meters per second, the gravitational field of the Earth, and a distance, well, I'm not going to use this quite yet. I'm going to do that d max. So what I did was I took that formula we just looked at. Again, I should have, on the previous page, and I plotted it. So this is what v naught squared over g sine of 2 theta looks like. It's a sine function. And it's a sine function, since it's sine of 2 theta, it's 0 at 0 degrees, but it's also going to be 0 at 90 degrees. So 0 and 90 degrees, it doesn't go anywhere down range. If I fire the thing at 90, it goes straight up and it comes straight back down. If I fire it at 0, it's at ground level, it just hits the ground immediately. So neither of those are what we're after. Now there's a Dmax, and I want to solve for the Dmax first because I'm a little curious here. The Dmax is 60 meters per second squared over 9.8. It says that this speed, this muzzle velocity, 60 meters per second, it could go, the projectile could go as far as 367 meters. So that tells us at what point targets are in range. So if the target is within 367 meters, it's in range. That would say that we can hit a target as far away as 367. Well, we're after 320, so yes, we can hit the target, but we don't want to fire at 45 degrees. The 45-degree angle will overshoot. We'll miss the target. So what we want to do then is, let's take a look. I think this is important. If the distance that we were given is bigger than V naught squared over G, there are no solutions. That would be, on the graph, that would be looking at something larger than where we've listed Dmax. So Dmax is that line at the top. Now this is something less than Dmax. That's something that we can solve for. And for D exactly equal to V naught squared over G, we have to launch at 45. That's the only angle that will get us there. But notice that if the D is somewhere short, there's going to be two possible angles, not one. So this is one of the nice features of doing some graphs. When you do graphs, you see things that you might not have anticipated by just writing down a bunch of formulas. This graph is clearly showing that there's going to be an angle somewhere between 0 and 45 that will get us out to 320 meters. There's going to be another angle somewhere between 45 and 90 that will achieve the same distance. Now, the shorter angle will get it there faster. The longer angle is going to go higher into the air and it's going to stay up there longer, but it should end up at the same distance in any case. Now what we want to do is to solve the problem. Let's take the formula from the previous page. Sine of 2 theta should be equal to dg over v naught squared. So I plugged all those numbers in, and I got dg over v naught squared is 0.871. And I took an inverse sine, and the inverse sine was 60.6 degrees, but wait a minute, we have to divide by 2. Remember, when we did that trig identity, that introduced a 2 theta, a factor of 2, into the sine function. And so dividing by 2 leaves me at 30.3 degrees. So that's the angle we want to fire at. Now, the graph is telling me if there's an angle at 30.3, really, that surprises me. Because that's pretty close to 367, huh? All right. Sure. Oh, I see. Yeah, it's kind of, the sine function is kind of flat at the top, so it's going to work. So we're actually up here somewhere, right? I didn't scale this quite right. So yeah, 30, why not? 30.3 degrees is theta 1. There should be a second solution over here by taking 90 and subtracting off 30.3 degrees. So the other angle we're predicting would work is 59.7. So for either of those angles, take your pick, if we launch this at 60 meters per second, we should end up with the projectile reaching its target. All right, questions on that? So again, projectile, projectile motion's kind of fun. You get to take a look at some of these problems with some pretty interesting setups. Okay, so we're going to take the football from a previous example, and this time we're going to punt this, instead of a kickoff from the ground. So when we punt it, it's already 1 meter in the air. How far does the football travel before hitting? Are they assuming the same speed? Huh. Okay, I guess they're assuming the same speed here. So that's what I assumed in solving it. So if we go back, if punting it, I don't think you can get the same speed from punting that you can get from a kickoff, but so if we assume the same speed, 20 meters per second, 37 degrees, height of 1 meter, what we're going to end up with is, okay, let's take a look at this. This is going to be a little more complicated. So for whatever reason, I decided to start with the coordinate system right where the ball was kicked, and then allow the ball to continue on to what I'm calling point B, which is below by 1 meter. It's 1 meter below where it was kicked. I could have done this either way. I could have started with this as plus 1 meter. I don't know, I tried this as minus 1 meter. So I'm going to say that I don't know what x is, but I know that y is minus h. And so what I ended up doing is, so here's the problem we're running into. We've already solved the problem where the ball lands at the same elevation as where it started. We know how that works. The time for that turned out to be 2 v naught sine theta over g, 2.46 seconds. But that only gets us to point D. It doesn't get us back down to the ground. So this is not a problem. This is a problem where you've got different heights where you start, where you end up, and the starting velocities have components. So it's a little more challenging than the other problems that we've looked at. So let's be a little careful here. What we're going to say is I'm going to pull out my formula for y and say what happens if y is not equal to y naught. What if we put in negative 1 meter? So I said h is 1 meter, and this is lower, so I put in the minus sign by hand. And I ended up with a formula that's a quadratic. I put it in quadratic form. And then I used the same approach that I used before. I've got a v naught sine of theta here, and plus or minus, over g, plus or minus v naught squared. Sorry, some of this I set up, it's not quite aligned the best, but I think that's working. Yeah, so this is v naught sine theta, v naught squared sine squared theta plus 2gh 1/2. So what's happening now is, before this h was 0, but now the h is not 0. And so with the h not 0, instead of just solving it algebraically right from here, I have to go through the quadratic formula process. So you can see that made a big difference in difficulty of the problem by putting the landing place and the starting place at different elevations and still giving them vertical and horizontal components of velocity at the launch. So anyway, I did the quadratic. We've got the formula here. I plugged numbers in. And what I found was the time to the top was still 1.23 seconds. That's what I was expecting. But this time, it's plus or minus 1.3. Now, if I take the plus solution to this, that says to come all the way back down to the ground is going to require 2.54. So what did that extra meter do? Well, launching from an extra meter of height increased the time from 2.46 to 2.54. It's only like, a tenth? It's not even a tenth of a second. It's like 8/100ths of a second difference to travel this additional short distance right here. So, yeah, so there's the additional 0.08 seconds. Now, where is point C? So I did this. I also created a point C that was at the same elevation as point B. Now, point C never happened. Point C never happened, but my solution, using the quadratic, my solution is saying that there is another solution where the time was negative 0.08 seconds. What is that trying to tell me? And what it's telling me is if I take this projectile motion, if I take this trajectory and I run it backwards in time, and then I run it back beyond where things actually started at point A, there is another point that lines up which would have occurred 0.08 of a second before. Okay, so that's what the quadratic solution is telling us. So I know a lot of times in math classes, and in physics classes too, we try and just go, okay, one of these solutions is good, one of them doesn't mean anything. In a lot of cases, they both mean something. And in this case, all we've asked it to do is to find out when this parabola crosses this value of y. That's all we've asked it to do. And so it's saying not only does that happen at point B, it also happens at point C. And in terms of the timing of this problem, point C would have occurred 0.08 of a second before the ball was kicked, but that never happened. Okay, so it's going to be one of those movies like Tenet or something, where with time reversal and anyway. So the distance that this travels, what was the distance before? It was like 39 point something. Look, we're going to get an extra yard because it was launched 1 yard above the ground. I'm still a little skeptical that you can punt with the same speed that you can do a kickoff. Anyway, that's what that 1 extra meter did, and it was miserable, right? When you think about this, that made it a lot harder. Okay, here's an even more challenging problem, I think. And so what's happening here is we got a helicopter coming in with some initial speed. The idea is the helicopter is going to drop a relief package for the people that are stranded. They're mountain climbers on a rocky ridge, and the helicopter's coming in 200 meters above them, and the helicopter is going to fly horizontally. I mean, it is a helicopter. Can't they just hover over the people and then drop the stuff straight down? Doesn't seem like it was much of a challenge for that. So the helicopter's going to try and do this. They're going to try and travel with a speed of, what? 70 meters per second? That's like 150 miles an hour or something. So the helicopter is going to try and come in at full speed, and then rather than stop, it is a helicopter, rather than stopping and hovering and just dropping the packages, they are going to go as fast as they can. Now, I don't know, maybe when you're dropping packages that's good. If you give it some forward speed, maybe when it hits it tumbles instead of just flat impact. That could be a feature. The other thing the helicopter's got to be careful about is they don't want to drop the supplies right on the people. It would be better to have it land somewhere where the people could go and get the supplies rather than have them come right down on top. Let's see, how far in advance of the recipients should the packages be dropped? Now, this is an easier one. Here, we're just going to let go of the packages, and they are going to start with a horizontal velocity, and then it's going to follow a projectile motion path and land, and that wasn't as difficult of a problem. Now, it says that for this problem, we want to find out what the distance and the time are in advance when we want to launch this. But here it says, ooh, we got to a point where 400 meters away. What angle should we throw this at? So a couple of fairly different set of numbers to work from. What speed does the package land? Okay, let's try this. And so this looks like it could be fairly challenging. So here's the helicopter. It's not a bicycle, it's a helicopter. So here's the helicopter, and it's going really fast, 70 meters per second, 150, 160 miles an hour, probably, maybe more. Let's go ahead and say x naught, y naught is equal to 0, right at the location the package is released. Now, I'm going to call downwards, I think, I'm going to call downwards positive. So let's just call this direction positive and this x direction positive. And I think that's going to keep everything positive through the entire problem. So I think we can do the whole problem with positive numbers on this. So h is at 200. We're trying to find out what d is equal to. V naught is 70 meters per second. So again, if we just let the package go, we just let go of it, it's moving forward. It's part of a helicopter. We let go. It's going to have an initial velocity in the forward direction that is 70 meters per second. Okay, so let's see what we've got here. We need it to drop a distance of 200 meters. Now, our formula for just dropping from rest, so the initial velocity in the y direction is 0. So we can use our formula for 1/2 gt squared, solve for t, plugging numbers in here. It's going to take 6.39 seconds to drop if we just let go of it. So if we just let go, it's going to take 6.39 seconds to drop the 50 meters. Is that right? Okay, seems to be 440, yeah, okay, seems good. Now, how far out ahead of that then? If we have to drop at 6.39 seconds in advance, and that means we need to launch or let go of it at a distance of v naught times t. The helicopter is moving forward, the package is moving forward at that speed. That means we have to drop it at the 447 meter mark. So I vote for that. I vote for let's let go of it at the 447 meter mark. Now, they decide instead they're going to end up throwing this downwards to shorten the time. Is that the idea here? So we're going to throw this thing downwards. They're going to start at a distance of d, which is 400 meters. So I've moved on to the second part. I think it was part A and part B. So if we miss the 447 meter distance, and now we're down to 400 meters, oh, we got to shorten the time. Exactly. Okay, I got it. So at 400 meters, we're going to have to shorten the time because we don't have time for it to drop. So let's throw it downwards. That will shorten the time. So I guess one of the questions is, do you want to throw it up or do you want to throw it down? And if we were more than 447 meters away, we could have given it an upward boost to keep it in the air longer so it could go down range farther. But we're too short. And so what we want to do is shorten the time and give it a throw downwards. And when we throw it downwards, let's see, we want to travel the 400 meters we're traveling at a velocity of v naught, so the time is going to be 5.71 seconds. So we can use the horizontal motion. We can use the distance and our speed to determine how much time do we have to get this thing down to the mountaineers who are stranded or something. So once we know how much time this is going to fall in, then we can plug that into our y formula, and we can plug the time in. Now, what we want to calculate from this is we want to calculate an initial velocity in the y direction. The v naught that we had over there, that was for the x direction. We need a subscript y on this because this is for the y direction that we're looking at. Okay, so this is a little weird, but we're going to take this entire equation and solve it for v naught because we know the y value. That was 200 meters, right? Yeah, the y is 200 meters. And we know how much time we've got to get there. So solving for V naught, plugging all the numbers in, it says we need to throw it at 7.05 meters per second downwards to have it reach the mountaineers who are stranded. Okay, or we could slow down the helicopter. Okay, which again, that's the one I vote for. Let's slow down the helicopter and just hover and drop. The packages are not, they'll bounce or they're non-breakable, right? Maybe. All right, so that's a fairly involved problem here. Let's wrap up. I guess we've got a couple last items here. We're through pretty much chapter 3. We've done a lot here. We did all the vector stuff, right? So we did all of the vector introduction stuff, and then what we've also done here in chapter 3 is we've looked at accelerations in both the x and the y direction as a possibility, and then we've kind of landed here with projectile motion, and we've done a good amount of time looking at projectile motion. Projectile motion is parabolic. If we take the formula and eliminate t, we can rewrite it in terms of v as a function of x, and you can see that that's a formula for a parabola. Okay, and then we have some really nice pretty pictures here. So here's some nice shots of those parabolas. And you see these parabolas everywhere, right? Here are some water fountains. You can see these really pretty parabolas being set up with projectile motion of the water. Here are some sparks from welding. Again, these are just flying through the air following projectile motion. Here, fireworks. Fireworks is a bunch of parabolas, roughly. Okay, here's our actual last topic in the chapter, is relative velocity. So we've considered relative speed in one dimension. What happens if we do this in more dimensions? So let's look at a couple of examples with this. And this is a reasonably important topic, and we've got time, so we're on schedule with everything. So let's look at a couple of problems with relative velocity here. Let's say that we have a river that's moving. So we're going to say, ooh, the notation here is really rough. So this is the velocity of the water compared with the shore, compared with the earth. So this is how fast the water is moving, and it's, oh yeah, it says that. And this is the speed of the boat with respect to the shore, and this is the boat with respect to the water. Now, the way we can write this in vector notation is that the velocity of the boat with respect to the shore can be written as the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. So we're kind of linking those together in terms of their vectors. And so that's what we have designated here. Now, what they've shown here is the boat has angled itself. Why is it doing that? Shouldn't it just be traveling straight across the river at this point? Well, if it angles itself straight across the river current is going to carry it downstream. So if it needs to land right there, so if it's saying, hey, I want to take this boat and I want it to land on the other shore right across from me, then going in this direction, orienting the boat, it's not going to work. The water is going to carry the boat downstream. So instead, what the boat is doing is it's angling itself towards into the water a bit. What that will give it is, if we can think of this, it's going to give it two components. The boat needs a component at velocity in the upstream direction to offset the velocity of the water. So the boat needs to offset the velocity of the water so that it won't get pulled any farther downstream. So it's going to have one component offsetting the water velocity, and one component of its velocity will lead it across to the other side of the shore. Okay, so that's kind of the idea here. Now, that means it's going to take longer to get across, because instead of the boat taking its full velocity and angling it towards the other shore, it's using part of its velocity to offset the current. Now, if the boat just wants to get to the other side fast, and it doesn't mind getting pulled downstream, the boat could just angle itself across, and then what will happen is the water would carry it downstream, and maybe it lands over here. But you can't do that for very long if you want to take the boat over and back and over and back. You don't want to keep getting carried farther and farther downstream each time. Okay, so here's the idea. What we're going to do is angle the boat upstream a bit. The boat's still speed in the water, we are told, is 1.85 meters per second. The speed of the current is 1.20, so I think it's doable. The 1.85 is bigger than the 1.20, so the boat's got enough speed that it can offset the current and still have some speed reserved to get across to the other side. What angle should the boat orient itself? And you go, well, let's solve for the right triangle. It's a right triangle. We want the boat's velocity to be here. This is the speed of the water, so this is going to be the 1.2. So the 1.20 is going to be this vector, and then we're going to have this vector as 1.85. So 1.85 looks like our hypotenuse, and 1.2 looks like the opposite side. So here is the setup. And so here's the triangle that I wrote down. And then I dropped all the vectors and I just said, you know, it's just a right triangle we're solving for. So let's see if we've got the right trig functions here. I think I want to use the sine because the sine would be opposite over hypotenuse. Yeah, this is opposite over hypotenuse. I did the inverse sine. Works out to be 40 degrees. That's pretty steep, right? So I really have to tip this boat upstream at a pretty large angle in order to cross the river straight across to the other. Oh, see, so I put a dock over here. So there's a dock here, there's a dock here, and we need to land at the other side where the dock is, so the water's deep enough and we can tie up the boat and get out of the boat onto the dock. So just how fast are we traveling? And to solve for the speed at which we're making our way across, we can take the hypotenuse and square it, subtract off the opposite side, square it, take a square root. It says that we're going to make our way across the river at a speed of 1.41 meters per second. So we're not going to go at as high speed as we would like. If we just turned the boat and went, 1.85, we could go faster. We could use the full 1.85, but again, we'll land farther downstream. So what we've done instead is used a 40-degree angle to offset the speed of the water, and then we're still going to be making our way across at 1.41 meters per second. So the time it's going to take us is d over vy, and the y component was 1.41. That's going to take 78 seconds. So I'm guessing that could have been shortened by how much? The 185 is larger by 20, 30%, 25%. So we could have gotten there in a reduced amount of time if we had done that. Okay, now here's the other situation. So maybe we do get to come back and do this. So the same boat now heads to, so the same boat's going to head directly across. What happens in this case? So let's do the very same thing. This time we still have the same speeds, right? So I've got a triangle again, but this time what we've got is the boat with respect to the water is heading straight across. It's not compensating for the current, so the current's going to carry it downstream, and the result will be a velocity off in that direction. Now for this triangle, did I write the numbers in? Okay, so this side is 1.20, and now this side is 1.85. This is going to be the hypotenuse. That's something we got to go in and calculate. And so, so this time it's going to be a tangent function that I want to work from. So the angle that the boat will be carried as a result. So what I'm doing in driving this boat is I'm just looking opposite shore, and I'm just trying to look at the shortest path to the opposite shore, and meanwhile the current is carrying me downstream. But I just keep looking at the opposite shore because eventually I'm going to get to it. So what this turns into then is a 33-degree angle that we are traveling at. So the net effect is that our velocity is now 33 degrees off course. And what's going to happen now, though, is we're going to get there faster. If we use the full 1.85 to get to the other side, it's only going to take us 59.5 seconds to get there. Now, what happens, that's like a minute, what happens during that 60 seconds in the x direction, and it says that we are going to land 71 meters downstream. So that's pretty significant, right? If we're going to be 70 meters downstream, that doesn't sound like a good idea. But anyway, those are the two options. So, you know, look at the page, the problem before. These last couple of problems here are pretty interesting. Okay, here finally, there's a couple of cars approaching an intersection at a 90-degree angle. So two cars are approaching a street corner at the same speed. They're both traveling 11.1 meters per second. What's the relative velocity of one with respect to the other? They're gonna crash. Shouldn't this problem be saying something like stop? Shouldn't this be a problem on braking distance? Okay, anyway, the relative speed means this. If I'm in car number one, for example, I can imagine myself at rest. So if I'm in car number one, I see all of the outside coming towards me. What were the speeds here? 11 meters per second. So I see everything outside of me coming towards me at 11 meters per second this way. Plus this car has got 11 meters per second of motion this way. Now if I'm in car two, I see the opposite. So if I'm in car two, traveling at 11 meters per second, I see everything in front of me coming towards me at 11 meters per second, and it's going by. And then I also see a car, which is part of that, coming, moving in the y direction, I'm going to call it, at 11 meters per second. And that's what this is showing. So that's saying that here is the speed of the car with respect to the pavement, and this is the speed of the pavement relative to the driver. Driver 2 is imagining themselves to be at rest. And by adding those 11.1 meters per second, we should be able to get the relative speed. Now, the angle here is at 45 degrees. We can see from the two velocities. When we square these two, we are ending up with 15.7 meters per second at 45 degrees. So that's what, again, driver of car 2 sees the entire outside world, the pavement, the buildings, moving towards it and going by at 11 meters per second. And then it's got this other object moving sideways through that at 11 meters per second, and we can add those two effects together to come up with that number. All right. Okay, we did it. We made it through chapter 3. Here's a summary. Here's all the topics. That's a pretty short summary. So projectile motion, relative motion, using vectors to keep track of different components of, or keeping track of different components of vectors and ways to combine velocities and accelerations. Okay. All right, any questions on anything from We've gone through 2 pretty substantial chapters now. Chapter 1 is a distant memory. So Chapter 2 and Chapter 3, make sure you're staying caught up with all of the homeworks. They kind of build on each other. Chapter 3 is kind of an extension of Chapter 2. We are now ready. We're going to move on into Chapter 4 and 5. Chapters 4 and 5 are introducing forces. So now that we've got the motion looked at, we can bring in forces and find out how forces acting on objects determine what their motion will be. So again, any questions at all, stop by office hours. Hope to see many of you there.